So thank you to the other speakers for already cutting the grass away. But I will now give my Technolution perspective on a lot of topics that already passed this stage. So as Boris mentioned, I'm currently business developer at Technolution. Technolution is a Dutch company, about 300 people. We call ourselves an innovative technology company, and we integrate technology into products for high-tech equipment markets, for space, for defense, many. Already in business for 38 years, and we are fully independent, which is nowadays important if you look to Dutch sovereign solutions or European sovereign solutions. This is the picture I really like. It's a Silicon Valley style. Our founders of the company 30 years ago started somewhere on the attic, and our CEO is one of the founders, and he's still in the company. So we develop advanced electronics and embedded systems. I will not go over this, but we combine embedded software, embedded hardware, high-speed electronics design, and I mean 50 gigabits per second, for instance, programmable logic, vendor independent, with good systems engineering, and we develop solutions for our customers. So we actually do projects for customers, but we also have some own products. And of course, to stay ahead of the competition, we do a lot of research and innovation. About 15% of our revenue is invested in research. What we also have is we have our own trusted assembly line, so we can really produce highly classified solutions for our customers. RISC-V already started for us more than 10 years ago. We are one of the founding members of the foundation. And it was because, as I said, we develop supplier independent programmable logic designs. We use FPGAs a lot, not only for prototyping, but also in real products, which we sell in relatively high volumes, but not that high volumes that you can afford an ASIC design. And of course, we all know that FPGA are really high performant at the moment. So we had a need for a soft processor IP that we could easily port to all kinds of technologies. And since we are working in classified security domain, it was also important that we had a processor IP which we could rely on. So which is developed 100% with Technolution. We have no dependencies on open source implementations, which makes it easier to get the product validated by security bodies, for instance, or to adhere with certification bodies. We have a product line for secure line encryption, so say hardware VPN solutions, which are classified Dutch, NATO, EU. And what we actually see in there is that it's mainly FPGA based, of course, Tempest proof, but RISC-V is used in the control flow. So software is running on the RISC-V processor, and the data encryption is done in the logic. So we have a lot of accelerators, and we use the RISC-V as a microcontroller to control the entire system. Actually, separation of concerns, so there are more microcontrollers active in the system. And as you said, we have full understanding of our custom implementation. We can offer the transparency to the customers and to the evaluators, and also portability, lifecycle management is important. We can port the same VHDL code, we can use the same compiler tools and use the same applications on every device. As Gianluca mentioned, we can also bring the experience that we have from the security domain, from the classified security domain, into other domains. And a couple of years ago, we started to think, and we also suggested to ESA, can we bring this RISC-V expertise into space? So what we see in space, and what we also see in new space and small satellite platforms, that there is a trend of more onboard data processing in space. There are a couple of instruments connected to a space platform. And what becomes more and more important nowadays is also that you need to protect the data from the instruments. So data signage is also an important aspect. And we actually saw a need there to develop an instrument control unit for this kind of applications. We talked to instrument developers and they said, yeah, they really have a dependency on the platform. So could you provide a solution where we can develop an instrument and we do not have a dependency with the platform anymore? Then you can already start the implementation of the instrument, the validation of the instrument, have a quicker time to market, a quicker time to orbit. The trend of edge processing, the data rate and data bandwidth are limited. So if you can do more in space, you can also reduce the latency of your applications. And it would be cool if there is a, say, generic but flexible instrument control unit that could connect every kind of sensor to a platform. And then if you talk about multi-instruments, it becomes more and more important that we can separate the data streams from those different instruments, because you would like to know that nobody touched the data, so you should already protect the data at the source, so in the satellite. So we proposed what we call CDPU, Control and Data Processing Unit. We proposed this as a modular electronics concept to the Netherlands Space Office. We did it together with the Netherlands Aerospace Center, and we actually built a prototype which is FPGA based, polar fire FPGA in this example. And we showed that with modular electronics, using an FPGA with a RISC-V inside, we could actually connect instruments to satellite platforms. As already mentioned, modular electronics to bridge the sensor with the satellite platform. And yeah, if you have the modular electronics, you can also benefit from reusing modules, so that it will give a benefit on cost sharing, and you can produce electronics in higher volumes. And the instruments developers are happy because they can reduce their the build time of the instruments. They can already start rapid prototyping using this platform, and we have chosen components that we can use as design in as radiation tolerant, radiation hard, or commercial. So you can scale also to the profile of the mission. I need to speed up. So what's inside the FPGA? There's a RISC-V based system. That's Technolutions Frinox RISC-V, and we have extended the RISC-V system on chip with streaming buses, so that we could also connect data accelerators to it and have space wire and space fiber interfaces. And then on top of the RISC-V processor, we run software. At this moment in the demonstrator is bare metal. This is our model setup. We tested the design with an engineering model that we got on loan from ESRON, the Dutch research organization for space. And it's actually an engineering model of the SPEX-1 instrument that's currently flying on the PACE mission. Have a full setup. We can set the sensor in data acquisition mode. We can do data processing on the CDPU and show that it works. And now we will start a GSTP element 2 activity, where we really will develop an engineering model and a flight model targeting CubeSats, but also targeting small sats, where we also will envision the advanced data handling architecture in the end. Currently based on a PolarFire FPGA, but we also have the expertise with NanoExplorer already, so it would be really cool to see whether we can have a full European components instrument. Tristan was already mentioned. We have a lot of research partners, so we also do research in the Tristan project, and especially I would like to mention our collaboration with the University of Twente. RIRI was mentioned. Together with the University of Twente, we have investigated a reduced RIRI implementation. There is a poster at the poster session, and after lunch there is also a talk by Tijmen Smit, our PhD student, who is also sponsored by ESA. So Conclusion, we developed the advanced electronics. We already built high security and high reliability systems using the RISC-V, and our approach is to reuse modular electronics, and yeah, there you can benefit from it. So if you have more questions, it was very quick, but this is all I would like to say.